Welcome back to the next tutorial, to the next solutions of tasks. This time we will have a look into questionnaire or into task setup which is not directly connected to the project, but I choose these tasks because working on graphs and finding solutions for graphs will come in any case in other lessons, and because here at this solution we'll have to use something where we require the use of functions, and therefore we can train a little bit the internal character of function. So the task which we wanted to solve is the house of the Nikolaus. The background is that the kids in Germany paint this house of Nikolaus, and they say this sentence: "This is the house of Santa Claus." So they want to draw this house without an interrupt. They don't want to draw a line twice, and there are several solutions to paint this house. And this house is nothing more than a graph. So you have here at the endpoint, at the edges here, or at the endpoints of the, or connection points of the lines, you have the states or the nodes of the graph, and these lines in between here are the edges. And therefore you have nothing more than the situation of coloring a graph. So you want to find a path through this graph, which is exactly a solution of an Euler way. And therefore you want to find all of the solutions here. So the first task was that you should train a little bit your painting abilities with Matlab, so that you have the same axes and also things like that, so that the house looks nice. And you should draw one solution which you prepared before. So is nothing more than using the function plot. And the next task is then for training the abilities, the things which you need for using functions. And functions have a very specific principle, which I explained in the theoretical lessons about Matlab. Function use a local memory. So if you have a script, everything what you create in the script will exist also after the script. Everything what you create in a function will not exist after the script, as long as you don't use a return value where you return a result to the caller of the function. The memory in the function is local, and this principle can be used to solve such a search mechanism, which is called a backtracking algorithm, or deep search first mechanism, in a very efficient way, because you can always make a decision which is the same here, 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 and here, and so on. At each node you have the same decision. You can select one of the not yet passed lines or ways. And therefore, if you do this, you change the arguments which you hand over, and if you call always the same function, so you call yourself, then you can have a very, very short program, because it's just one function which you call also within, or again within the function itself, and with another argument, and after a special end criterion you jump back and you take with you what you need, and therefore you have just a function call. Okay, it sounds a little bit strange now. Therefore, I want to bring you back the idea of function and what happens if you call the same function again, because it's comparable with the staircase. So let's have a look into this principle. Recursion is something like walking on staircases. It's a nice image which you can keep in mind if you do this. So each time you step up to the next step is a function call, and the function is the same which you're currently in. So you call yourself, and then at each time you can take something with you. It's the argument which you hand over, and then you jump to the next step and the next step, and each time if you step down, then it's something like losing the information which you leave there. So you have to take things on the way back which you want to use later on here on the lower ground level. So let's do this. I want to show you a sample. So let's start with the sample that we have a number 2, which we take with us to the processing up to the staircases. So what I do is I pack this number into my bag. So this is the argument, and then I woke up. So let's do this. I jump up to the next step. It's the function call. So if I'm here at the next step, I can use this what I have in my bag. So I again use this, and in my case I multiply it with 2. So the result is 4. So at this level the result is 4. What happens is that there at the lower level, before the call happened, everything is already in the memory. So I have a new memory level, a new stack level where this information is now available. And this is because the function, or everything what happens in the function body, is a local memory. So if I jump to the next level, I have a new local memory. And if I jump back, I lose this local memory. So what do? I call the same function again. So I call myself again. I take the 4 now with me up to the next staircase. So let's do this. I take this and put it to the next staircase. So I call the function again and I jump up. So at this level, I take my argument again, put it out. But at this level, from there, I took 4. So therefore, at the next level, at the next local memory, I have the 8 here, because I do 4 times 2. I do the same calculation again, and I step up. So I do the same thing again. Let's take the bag, and let's jump up. Same again, and again. So I can always use what I have in my bag. So remember that all of the steps down here are in the memory now. So if I return from the function call, I forget this here, and I will come back to the level which I reached, so to the memory state which I reached. So all of the staircases which I climbed up are something like elements on the stack. So I put a new element on the stack, which is my function body, with everything, all of the memory elements which I created at this level. So if I return, if I step back, if I do this, I arrive here, and what I have is I forget everything what is here. So I really forget this stack element. So I'm back in my memory element which existed before. So if I do this again, and if I climb down, I'm back at the ground element, and at this ground element I have the existing 2 again. So this 2 which I used for the start. So everything what I calculated was done, but is forgotten now. So therefore, if I print, what I have available is the 2. So everything what I did before is forgotten. So only the existing memory which with I started exists. So that's the case for the memory in function. So if I want to take memory back, I have to do the same. So I climb up again, and here at this point I have to remember. So what do I have to do? I have to bring my result back to the lower level. So I have to pack it and I have to bring it back. This is the return. So I return now a value. So for example, here I return the 32 at this level. So I take it with me. Only things which I take with me, so which I return from the function, will be available in the lower steps of my staircase. So if I do this again, I have to take my back again, or my package again, back to the next level. So I forgot everything what is here. So the 16 is forgotten. But what I took back is the 32. Each time, if I climb down, I will take the result from the last level up to here. I take it back with me down the hill. And the same again. So if I have this away level, I have the 32 away level because it's here. It's in my bag. It's in the return value. So, and if I print this now, then you have the 32 available. And this is the really important thing what you have to keep in mind, that you hand over arguments. You can use these arguments. These arguments are available as long as you're in the function body. If you call the same function again, then you take everything what you hand over with the arguments again for the next step. And each time if you return, you forget everything because the stack will be reduced. So you climb down and everything what you don't take with you. So everything what you let there is forgotten. So everything what you want to use later, you have to take back. And if you're on a higher step here, and if you have a for loop, for example, and you call the function again with the different indexes or things like that, then at each step you do the climb up with different arguments. So the next step will be with the next index, for example, and the next step will be with the next index, but you always just jump from one level to the next. And at each time the new for loop starts. So for example, at this level, if you run the for loop, it starts with 1, then you climb up, it starts with 1, you climb up, it starts with 1, and so on. And at the end criterion, you continue with the loop, and then you climb down, and then you continue with the next index, for example, at this level. And then you climb up again, and each time, at each level, you do the complete for loop. And then you come back each time with the result, if you return it, or without the result. So if you have this image of a staircase or of a stack in your mind, if you do the programming of this recursion, then it will be a helpful thing that you can understand what your program does, and then you just can keep on this level. You don't have to think what happens there. You always do exactly the same. You just think what must be done on one level. So your function reduces. If you would write a for loop, for example, for the whole work, it would be much longer, much bigger, because you have to keep the memory, you have to reduce the memory, things like that. But with the function, it's automatically done. And therefore, you just have to think what is necessary at this level, and then you call yourself, and you do exactly the same on the next level, like we did here with the number 2. And then you do it exactly on the same level. You don't have to think, how do I climb up through the whole thing? It's just you call. But the important thing is that you need an end criterion. Otherwise, you would always climb up. So my end criterion was here, for example, if you reach a number larger or equal 32, and then you climb down. So you need an end criterion. And that's the big principle. So let's continue with some samples, or with a more detailed description of a simple sample. Keeping this in mind, I can give you a more detailed explanation of what recursion really is and how it helps us to solve the problem which is described here with this house of Santa Claus, or with painting or coloring these graphs. So therefore, I will give you a short intro, which I took from another lesson which I recorded, and this explains exactly the principle of recursion and the use for the house of Santa Claus. And then we'll try to write a program in Matlab which solves this task. Let's have a look into this recursion again with a simpler program which does not make sense in a real world scenario, but which will explain a little bit better what we do here. So what we do here is we have a function which is called recursive, and we call this function inside of our function again. Each time if we call it, we start with this element, this handover argument, and we add a 1 to this argument. And then we start a loop from 1 to 3. We always display what we have as an output and which step we are. And if we reach, so this is the clear end criterion of our recursion. So if we reach a situation that the call hierarchy is not anymore lower or equal to 2, so if it is, for example, 3, then we won't do this recursive call again. So we will stop and we will go back, jump back to this position. And if we jump back, as we have no return, so we don't return calculations which we did inside, we will jump to this level. Remember the staircase, so remember this step. We will jump to the step which we reached before. So everything what we calculated before will exist again, and the rest will be forgotten. So everything what we have done in the future steps, or in the following steps inside of the next recursive steps, will be forgotten. So what does it mean? If we let the program run with a starting sequence or with a starting number of 1, then we will start with call hierarchy 1. We have the loop counter 1. Then we'll jump into the next level. So we go to here, we have call hierarchy plus 1, so we'll have call hierarchy 2, and we'll run again to here. So we will start again the next function. So the loop will not continue. So it will just continue if we reach the end criterion. So the first steps are we count the call hierarchy 1, 2, 3, because these are the calls. So we have now 3 calls of our function. And if we reach the call hierarchy 3, then the loop starts. Our call hierarchy is always 3, therefore the loop will always continue. So we'll have 1, 2, 3. And then we finish our loop. We go back in function. So therefore, we jump back 1 step down, and 1 step down we had the call hierarchy 2. So here we have the call hierarchy 2. Call hierarchy 2 is again plus 1. So we go plus 1 is 3. And then we start our loop again, and so on. We do this as long as we finish our complete run. Important here is that you get an idea of what happens, and I think this staircase, these steps, are quite helpful, because each time if you step down, you will reach the situation again which existed before. Each time if you step up, you start a new processing, so you start a new calculation. And if you don't return things which you created in higher steps, you will lose them. So if you return them, you can keep it. Each time you jump back, you forget everything what you did in the higher steps. Okay, so therefore this is a recursive call of the same function. So you call the same function with a new argument, and each time if you come back, you will lose everything what you did, and you will continue at the step where you are with the next calculation, for example. You can use this method also for finding paths through a graph. And one very nice simple sample is this graph here, which is called the house of Santa Claus, because the children in Germany paint this on Christmas time, and they try to find a way through this graph. So they want to paint this house here with a method so that they have a continuous line. So they don't want to interrupt the painting, and they don't want to draw a line twice. So they start somewhere and they have to follow in one drawing the whole line. And they say, this is the house of Santa Claus. So, but this is a nice sample, because what you do is you start and you do at each state here, you do exactly the same decision. So I want to show you this. So if we decide to start here at the lower corner, at the lower edge here, then at this point I can make a decision. So I can go one way. So I can go up, or I can go here, and I can go here. So if I do a decision, then for example, I decide to go this way. So let's do this. Let's move up. So at this point, I do exactly the same decisions again. I know that I came from here, but I can go this way, or this way. So it's at this point here, I do exactly the same decision what I did at the previous step. And therefore, it's predefined for this recursion method. So let's do another decision. I want to go this way. So if I'm here, the same. I came from here, and I can make a decision. So if you remember, I always go, or if you watch this, I always go onto a direction which is not yet marked. So I remember, at each step for the next recursive call, I remember which direction or which line or which edge I already passed. So this is already marked, and then I go one of the edges which are not yet marked. So in this case, I just can go this way. And at this point, I do exactly the same. I know that I came from here, and I can go to here, or to here. So this is what I do. And at each point here, I do exactly the same decision. So I move through this graph, and at each state, I make the same decision. Each of this is one call of the function. So I call myself. And now I'm at a position where all of the graph edges which connects to me are marked. So I have no chance anymore. So this is my in criterion. And I found one solution, because I found one way completely through this graph. And what do I do now? I go the step back. So remember the staircases? I go back, and at this jump back, I come to a situation again where the memory is like it was before as I was there. Okay? So what I have to do is I have to remember the path here so that I can use it later on. Because, for example, for the output, so if I jump back, I forget everything. So everything what I want to remember, so for example, that I found a solution, the counter for the solutions, and also maybe the path through this graph, I have to remember. And now I do a step back. So I go back to this point. So going back means I return from the function. Going back means going one step down. And I do the same again. Return, because at all of these positions, I just find solutions which I already have. So I have to remember where I came from, and I have to remember, or I have to check which positions are marked. At this position, I cannot go to here, I cannot go to here, I cannot go to here, and I came from there. So everything is already clear. I do this again. This is this jump back, this back step or step back. And here's the same. I came from here. I cannot go to here. I cannot go to here. And again, jump back. So here at this position, I can start my recursion again because it's the same decision as before. So the only difference, or the only thing what I have to remember, is that I came from here, and then I do the same decision. So this is already marked, so I just can go to here. So what I do is I jump to here, and then I continue in the same style. So this house of the Santa Claus is very connected to a thing which is called Euler's Königsberg bridge problem, because Euler defined this problem, and it's that you have here some islands. So here are the islands, and you have bridges between these islands, and you want to pass each bridge just once, but you want to find one path, one complete way, a so-called Euler way through the whole graph. So if you watch this, it's exactly the same. So let's start here, for example, at this island, and then I can go 1, 2, 3, 4, 5, 6, 7, 8, and I passed all bridges just once, and I found one way through this graph. And this is the Königsberg bridge problem, which is really nice connected to this house of Santa Claus. So Euler described such a situation in the year 1736. He found a proof that it is solvable if if one island has an even number of connections, and then this is called an Euler way. So what we find here is an Euler way, and if it ends up at the same position, at the same starting point, then it's called an Euler circle. And this is the traveling salesman problem, or the Chinese postman problem. So if you pass all of the elements, and you end up at the starting point here. So with this, you can solve all of these possibilities just with this backtracking algorithm. And therefore, it's very similar to this sorting algorithm. And it's a nice, effective way, but it grows with the problem size, of course. So if you have large graphs, it will not be very efficient anymore, because you find all of the solutions. But anyhow, you want to find all of the solutions. So you have to do all of the solutions. Compared to some optimization algorithms, for example, for navigation, you have then graphs which have weights on the edges and things like that, so that you have other decisions, and then you can find optimized ways. But anyhow, you always do the same decisions at the same, or at each point, and therefore it's again the same type of behavior. So this is just to explain what the backtracking algorithm here in this method of the depth first search does. We start with the first starting point, so we have to do all of these things for all starting points. If you remember, we started on the left lower corner. We have to do it for all of these for all of these states. So we start for all of these, but it's a loop over all of the states or nodes, and we start with the first starting point at the current position. Then we call the backtracking function, and then we go through all of the possible lines. We mark our lines, so we have to remember, we have to return things which we already marked, where we came from, and then if the current point fits to one of the current line endpoints, then we draw the line and set the corresponding line at a new way and go to the new point. The new point is then defined as a current point, and with this current point we go again into our backtracking function. So we call the backtracking function again and do the same again. If we don't find a possible way anymore, then we return. And this is our end criterion. And therefore you will have this way, which is very similar to what you saw from this simple recursive call. So each time if you jump back, you end up at the position which you had before. So everything else, what you did in the other steps, in the higher steps of our staircase, will be forgotten. So therefore you have to remember, and you have to remember the path which you found to give it back to your user and to tell the solution. Here with an output of a colorization. So you have the starting point here on the left lower corner, then you go up, right, and so on. And if you find a solution, you remember the solution, and then you go back and you try to find a possibility again. So as you did this before, you don't do it because you go to the next possibility, and you go back, you go back, you go back, as long as you find a new possibility. In this case, you came back from here, so you don't go this way again, but you have another possibility. You can go up here, and therefore you continue again with a forward step again, and then you go backward. So this is this backtracking algorithm. You can solve several problems of this. For example, you can find, or you can solve this Queen's problem, which you find in the lesson about style guides and things like that. So it's always the same class of recursion. And if you do all of this, you will find 88 solutions after scanning of 1100 lines. If you watch the graph, you can improve this. If you find symmetries or whatever, then you can reduce the problem size, and therefore you can speed up your code tremendously. Okay, so you don't have to search all of the possibilities. With all of this knowledge, we can now start to solve our tasks. So first of all, we can do this simple task, drawing the first solution with a predefined path through this graph. So you can train it on your sheet of paper, and then you can just plot it with the functional line, for example, and then we can continue with this. So let's directly go to the Matlab program, and let's do the programming of the first task. If you watch this graph, you can use a line function which draws this line, 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 and this line. So the line function, if you don't remember, watch the video about this in the theoretical lessons, uses the x1, y1, x2, y2 in a combination where the x points or the x-axis parts are in a vector and the y-axis parts. So line in a vector x1, x2, and y1, y2. So therefore we need the definition here. For example, in this case 2, 2 and 2, 8 is the first line. And then 2, 8 and 5, 11. And then 5, 11, 8, 8, and so on. So what we can do now is we just create a matrix which defines these lines. So each line in the matrix is the x1, y1, x2, y2 of this line. So if we do this, we can simply make the following. We define a house graph, and then we say 2, 2 to 2, 8 is the first line. So 2, 2 to 2, 8 is the first line. And then the next line is 2, 8, 5, 11. 2, 8 is this point, 2 in the x-axis, 8 in the y-axis, 5 in the x-axis, and y in the 11 in the y-axis, sorry. So And with this, we can create a complete matrix which represents all of our lines. So remember, it's just x1, y1, x2, y2. So if we want to plot this first line now, we have to take this and this as an x1, x2, and this in a vector as a y1, y2. And then we can use the normal line function to draw this line. So before we do this, as in each script, I start here in Nicolaus step by step. We do a clear all, close all, and CLC. So if we run this, we will have the function available that it creates the house graph. Sorry, it's not a function, it's a script, of course. We have the script available which creates the house graph. And now we can use the line function to create the different lines. So it's quite simple. What we do now is we create a line function where we take for the x, for example here, this element and this element, and for the y's we take this element and this element, and this is our first line. So if we do this, you will see that we create a plot. So, and with the same situation, like here with the same calls, we can draw all of our other lines. So we make hold on, and we draw our other lines. The next one, we just have to change the index into our matrix. So we're now going to the next line, which is the next line in our graph. And then we go into the next line. And the next line. And the next line. And the next line. And so on. So see what I do manually here is predefined for a for loop. Because we just change always the index here, and it's quite nice. It's a counter or an index change through all of these indexes here of the lines of the rows. So we have now this nice plot, and here is our program for this plot. So we can copy this, and we copy it into our program. So if we create figure here, then we have the program which creates our task program for the first task. As I said, this is a predefined situation for a for loop, so therefore we can change this to a for loop. So let's create this for loop. It's quite simple. We have a for loop. We use a new counter or index iterator. We call it line count, and it goes from 1 to size of this matrix house graph, and I take the first dimension of this. And then I just have to use one line call here. And instead of individual indexes of the lines in the graph, I use this line count here. So with this, I have everything what I need for the drawing. So let's run the program. You see, everything works. So what I can do in addition to that is that I beautify this. So for example, I can change the axis. So if I go back to this and if I watch this, it would be much nicer if it is equidistant and if I have it really with some borders around and things like that. So we can do this in a very simple way in Matlab. So we already remember the x-lim and y-lim where we define the limits. So if we do this, I can say I want to go from 0 to 10 in the x-axis, and I want to go from 0 to 12 in the y-axis. So if I do this and if I run the program, it will create this image. So now I want to change also that I see all of the ticks here, so all of these single lines, not only steps of 2 here. I can also change the scaling of this axis. So therefore we can add a change of the properties, and if you watch the videos you will see that we already used this once in the theoretical lesson. You can set the property of a special figure if you use the figure identifier, and here this is the current figure identifier, and then you have to set the property always with a pair of an identifier and the value. So in this case I set the y tick. The y tick is here the number of lines which are shown, these intermediate lines which are shown here, and with a x tick I can do this in the x-axis on the current image. So if I do this, you will see that we will get a new image where we have the individual ticks at each integer number. And then we can create an aspect ratio so that the house looks in the ratio similar. And we can do this if we set the aspect to 1:1:1. If you want to know more about these functions, then have a look into the Matlab help pages, because there everything is explained. So with the aspect 1:1:1 you set all dimensions x, y and z to 1, which means that if you have here for example a 2, it will be that one line in the x will be 2 lines in the y. Here we have 1:1:1, which means one line in the y-axis is actually the same like one line in the x-axis. So this is our drawing and this is our solution for the first or of the first task. So now we have to update it so that we can solve the, let's say, house of the Nikolaus. So let's continue with task 2. We want to solve this house of Nikolaus or house of Santa Claus. And therefore we have to extend our existing program and I want to plot all steps with different colors, and the decision at each point, at each state here, is the same, where we use our recursion. So I extend the program, the existing program which we created, and I will have to write an additional function which can be called recursively. So let's directly jump to the Matlab solution. Before I continue here, I want to replace this line function with a known line function, which helps me to simplify the output, so that I have a different bold style or line width and a different color of the line. You can of course use the properties with these property pairs, but I created an own function which is called T.S. Nikolaus plotline, where I have the same input like the axis, and I just define the line color and the bold style. So the color is the color which I plot, or before I plot I do a delete, which is white, and I plot it with a new color, and I do a bold style. So I always set the width of a line, and if it is 0, then I set it to 5. So I always set the width of a line, but if it is greater than 0, I use it for the plotting. So then I have the line width. Okay, so color and bold style gives me a possibility to set it with one call of this function, and therefore I replace this line function with my new function. So it will be then this one. So please compare. This is exactly the same like this. So it's like with a line function, and this is exactly this. So these are my x1, x2, y1, y2 vectors, and I just add the color and if I want it bold or not. So in this case, this is the new functionality. So if I run it, I will get the same output as before, just with another possibility. So for example, if I set it to 1, it will look like this. So therefore I can draw a different width of a line, which is predefined to 5, or I can draw it with a line width of 1. So in the first drawing, in the first output, I want it like this. So what else do I need? If I want to identify which way I want to go in the next step, I have to remember which line I already passed. So therefore I have to create an additional memory for the remembrance, or for the memory if this line is already passed. And therefore I do it in a very simple way. I extend this matrix with an additional column. I add an additional column vector at the end here as an additional new column to this house graph matrix. So this can be done very simple. If I create a new matrix where I combine the existing graph with an empty vector created by zeros. So I create a new vector which has the size of the house graph, the first dimension, which is the number of lines or the number of rows, and with one element in the column range, and I add this to the existing. I use a comma here so that it is in the next column, and I add this so that I get an additional vector where I can make some marks if the line is already passed, or if the way is already colored. And then before we start we have to do an additional thing. We have to find all starting points. So if you think about, you can use symmetries or things like that to simplify, because the house of Nikolaus here in this case is symmetrical, so that you just have to check this, this, and this, because this is exactly just a symmetry of the other edges. But in our case, we want to really do a deep search through all of these elements and therefore search all of these points. What we have to do is we have to run through this graph or through this description of the graph through each line, and all of these are points where we can start, and then we select all of them. So we create a list of all of these points here, and then we delete all elements which are duplicated. So all duplicates are deleted. So therefore I write a for loop which runs through this graph. What we do is, I know that I will end up with a number of start points, because I always have 2 points here, and therefore I will have the number of lines times 2 as start points in the beginning of the calculation. And then I will do a loop where I identify all of the start points. And this is quite simple, because I take the first point and I take the second point in this line. So why did I use this start point counter? Because I have to use 2 different indexes. The first index gives me the line here of the house graph. The second index, which I start with 1 here and which must always be the double of this here, gives me the position where I have to copy the found point to. And after this, I will have a list of all possible points where I have duplicates in. So let's run the program. If you check the start points here, you will see that now we have a list with duplicated points. And if we now can delete all duplicates, then we have all of the possible start points calculated out of our original graph description with the lines. Finding duplicates is also a really simple call of a Matlab function. So you have not heard before of this because we have not done this, but I always told you, if you have such a situation that you have to do something which you don't know at the moment, don't start writing your own program. Just search if there is already an available function offered by Matlab. And it is. The function is called unique. And what you just do is you assign the result of unique to the start points. You hand over the original list of the start points, and then you tell if you want to find unique or duplicates in the rows or duplicates in the columns. And if you do this, then, so I just copy here to the existing elements and I run it onto the existing elements in the workspace. And if I show this, then you find all of the 5 points which we will have at the start point. So watch the graph. These are the start points and the coordinates of the start points. So this is exactly what we want. And with this, we can now walk through all of these start points, and we can call a function which does the recursion. So before we do now the call of this function here, we have to create this function. And I prepared this function, and I will explain it here, not step by step, or I will not create it step by step. I will explain it step by step with an existing program. So what do we have to do? If we watch the graph again, we do at each point we do the same decision. So if we are here, then we have to find all possibilities. So we run through all of our lines here, and we check if the starting point, if the current position is either this or this, because we can walk the line in this direction or in this direction. Then if one of these points, x-y combinations, is the current position, and if it is not yet visited, then I can use it. And then I use the corresponding opposite point as a new current position, and I call myself again. So again, what I do, if I'm here, I check which possibilities I have. For example, in this case, from 2, 2, I can go to 2, 8, or I can go to 8, 2, or to 8, 8. These are these three lines. And then I follow this line. I use a new position, so I jump, I change the current position to this end point of the line, and then I call myself the function again and do exactly the same. So before I do this, I have of course marked this line as visited. So before I do the call, I have to set the marker in the 5th column of this house graph, which we extended, to 1, so that I know, okay, I have already visited it. Remember, go back to the staircase situation. If you go, or if you call this function, if you go one step up, then we'll take everything from the lower step to this higher step, and then we can use this. And then we start the same again. So we run again through all of these possibilities, and we check, is there a connection point? So at this step, for example, at the position 2, 8, we now check, are there connection points? So from 2, 8, we can go to 2, 2, so we can go backwards in this direction, but it's not possible anymore because our marker will be 1, because we came from here. We can go from 2, 8 to 5, 11, and we can go from 2, 8 to 8, 8, and from 2, 8 to 8, 2. So these are these 4 lines. So we have always taken into account that we can start from here, or we can start from here and go into this direction. And this we have to always visit, or have to always check, and we have to always check if it is already visited. But the rest is always the same. If we do a new decision, we select the corresponding point of this line, and we mark that it is visited, and we call the function again until we reach the end point, for example here, where all of the lines are already visited, and then we return. At this point, we can check if we reached a situation that all lines are marked. So at the end, if we do a return, or after the return, we can check if all lines are marked. So if the whole graph or the whole marker vector is with 1s, and then we found a solution. So we can remember the solution, we can add a 1 to the counter, and then we can go back. Going back, so returning from the function, after the return from the function, we have the previous situation. The only thing is what we have to change is that we cancel the mark or this visiting marker, so that we delete the last line again, and that we do unpainting. So let's have a look into the function. I prepared a backtracking function which is called his Nicholas backtracking, and what I hand over is the current position and of course the house graph. I also add if I want to plot or not. So all of these things here are just things which are in addition So for example, if I want to do a plotting, I have here a number which is greater than 0. I can select a pausing time, so that after each plot I have a short, or after each selection I have a short interrupt, a short waiting pause. I can also add the current path. I can add the found paths. So if at the end, if I want to remember all of the paths which I found, I can hand it over, because I have to add always a new path, a new found path to the list of paths, and I can count the number of steps which I did. So what I return is the current path, the found path, and the number of steps. So it's what I want to remember and what I need for the further operation. So in this case, you can ignore these figure selections. If you want to always plot it, then you can ignore this. But I select only a plotting if it is greater than 0. So therefore, I always do at each plotting, I do a check of the figure, for example, here and so on. So if I have to do a plotting, I always check if I want to plot. So ignore this if you just want to see the pure graph. And then I do exactly what I explained before. I go through all of the lines in the graph. So I go through all of these lines here, and I check if the current position which I got from here, and at each point of, at each edge, at each node of this graph, I do the same decision. So I have a current position. It depends on the previous steps, but for the calculation it doesn't matter. So I have a current position which is an XY position, and I check if the current position is either the starting point of the line or the end point of the line. And if it is a starting point or the end point of a line, then I can do a plotting in red. So I go this way. So I path this way. And I have to remember, so you can also ignore this pausing. It's just used for the plotting. After each plot, I will pause a little bit if I want this. But you just have to check this. So if it is a start point or an end point of the line, and I walk through all of the lines, then I plot it in red. And I mark this position where I'm at the moment, where I am at the moment. So at this current position, I mark as visited. I change the current path so that I have the current path plus the line count. And I change the current position to the, or I remember the previous position, which I take from the current position, so that I can jump back. It's used for the unplotting, for example. And then I select the new current position. So I remember the previous, I remember the current position with the previous position, and then I really go this way. So this is just for the plotting, and this is for my own bookkeeping. So I go here, I go this way. So for example, if the current position X and Y corresponds with the house graph 1 and 2. So with this, I will select this as the next current position. So I go this line, and if it corresponds to this, I will use this as the next position. I go in this direction. So the new current position in my case, if I start with 2, 2, and if I walk this way, then the new current position will be this. And this is exactly this selector here. And then I sum up the number of steps, and I call myself again with this new current position, with the same house graph, of course, and with the same things which I selected from before, just with some changes of the current path, the found path, and the number of steps. And if I call myself again, then I start here again. With the new position, I go into here, I do the same decision, I run again through all of the elements, all of the lines here. So I have a new state or a new level of my staircase, and I run through all of these elements again, and I do for all of the elements, I do the same again. And this is why it is a deep search or a backtracking. The backtracking comes now if I reach a situation where, for example, I I cannot find any more a following position. So if all of the things are marked in this case, so if I cannot find a new position, so if all of the lines are marked, I run through all of this and all of the lines are marked, I will end up here. So I will end up here, and then at the end of the for loop I will do exactly what I told you. I will remember the found path if all of the lines are marked. So if all of the lines have a mark here that, or if all of the lines have an identifier here that it was visited or that they were visited, then only if this happens, in this case, if the sum of the elements in the last, so I always set 1 if I pass it, if I color it. So if the sum of this colorization memory is the same then the complete size of the graph in the first dimension, so of the lines, then I will do the following. I will draw the graph completely with green. I will wait a little bit and I will redraw it with red, and I will remember the found path. So the current path, so the steps through the graph, the current sequence of lines will be then added to the found path, and this found path will be returned, and then we'll go through this and we will return the function. So if we return the function, we will come back to here. So we will go one step back, one step down of this staircase, and this one step down in this staircase will continue with the previous situation. Only things which we already return here will be used for the continuous steps, and then we will continue here. So we will do an undrawing. So we will mark the previous line, so the line which we colored here in red, we will color again in blue, because we have to go backwards, and this is this backtracking. And then we will change the marker of visiting, this identifier. If we have colored this line, we will reset it to 0. We will change the current path. So the current path, the end of the current path will be deleted. So the last add-on to the current path will be deleted, and then we will go to the previous position. Here we remember the previous position from the current position, and here we go back to the previous position. And then we continue. As long as we do not finish the for loop, we will continue with the next element on this specific level of our staircase. So if you always keep this staircase scenario in your mind, you can really nice identify where we are. And then we go to the second line, and for the second line at this individual level of this staircase, we do the same, and we go to the next step and we run again through all of the possibilities of the lines and so on. And therefore we always climb up, climb up, climb up, and climb down, climb up, climb down, climb up, and so on. Therefore it runs through all of the elements, and this backtracking mechanism calls always itself with new starting point. Starting point is always the current position, and it remembers things which we want to use later on. So try to use this program, try to understand this program, and then run it. Okay, so again, very simple in the steps, but very complex in the understand, because you have to think in this recursion method. So you call yourself and you create always a local memory with a new situation, and this is what you should keep in mind. So let's run this program. I cannot directly call it from here. I have to do it here in my program. So what I do here is I will create empty elements for the things which I hand over and which I return. So if you remember, these things which I return and these things which I hand over, I have to prepare here. And then I run through all of the elements which I have in the matrix, all of the points, of course. So this means everything what I created here, so the start points are this iteration points here. So I run through all of the points and I do nothing else than calling of the function. So again, it's like inside, I call this function, I hand over the first starting point which I take from here. It's just an index counter through the start points, through all of the possible points. I hand over the house graph which I created here with this extension of the identifier of if I visited it, so with this marker here. And then the rest is for the plotting and the rest is for the housekeeping. So these are the elements which I also get back. So here I have then a list of all found paths. Here I have the number of steps, and here I have the number of, or here I have the current path to remember. And then I can print this, and I will get the number of, or all possible solutions. So let's run the program. So what you see is now this backtracking, this green lighting and the red. This is this if at the end of our backtracking function, and you see it walks forward. Each time if a red line is painted, it will go step up in our staircase. Each time a red line will be cancelled and will be drawn with a blue line. Then it goes back to this and takes the, or replaces the current position with the previous position. And it walks through all of these possibilities, and at the end you will get 88 possibilities. So 88 possible ways. It will cost a lot of time here because I always have this 0.05 seconds of waiting time. So I will interrupt it here. And if I, for example, don't draw it, and if I have no waiting time, then it will run through the program. It will do all of the checks, and it will find all of the solutions. So if you want to also remember how many possibilities you find, then you have to also do a housekeeping of the number of possibilities. I do it implicitly because I collect the found paths, and then I can just use the size of found path, comma 1, and then I will have the number of possible found paths which I can go or which I can find in our graph. So therefore, I don't do an explicit housekeeping of my number of solutions. Okay, that's a very important mechanism, and this is also a very specific thing which helps you to understand the principle of functions, because in the next lessons we will continue with this. We will have to rewrite our, let's say, script step-by-step solution to a really sophisticated suite, to get a very flexible adaptation to new databases, to new data sets, and therefore we will have to use functions. And this task here is a really nice and helpful mechanism to understand the principles of all of the functions with this local memory, with all of these things. Okay, so therefore we will have to use this also later on, not with a recursion. We will use in most cases the function as they are, so the function will not call itself, but the principle of this local memory is the same for each function. So each time if you call a function and if you return from the function, everything what you create inside in the body of this function will be deleted. So therefore we will continue. The next step is the finishing of our project tasks. Therefore, I will show you a little bit of the future tasks so that you know what you have to do in the future. And then we will have a look into an optimization and an improvement of our solutions. So let's have a look what we want to do in the next tasks. The next task is that we want to adapt our aggregation calculation. Currently, so we jump back now to the project again. Currently, we have a fixed aggregation size or interval of 15 minutes. These 15 minutes are fixed, so we define it like that. And now we should improve it that we have an individual adaptation, so that we can have an individual plotting with an individual interval for the aggregation. For example, we want to use 5 minutes or 2 minutes or whatever. And what you will see is later on, if you plot such a nice color plot, then you will see that you will also see the shock waves which propagate through the congestion situation. And this is the first task. So optimize and adapt the aggregation calculation that you can use different interval lengths so that you smooth your data or that you go to the raw situation. And the next task is then the final task. So with this, we finish the whole programming in principle, because then we start just with optimizations. Then we will convert the scripts into functions so that we will prepare a suite which can be used also for other input situations from the raw data scenarios. And therefore, finishing the program will be plotting this nice color plot, this contour plot, which tells you that at a specific time you have the situation of this speed setup, and the third dimension is here represented with a color. So this third dimension is here the speed, so that you have the x-axis is the time, the y-axis is the distance, and the z-axis is the speed. The z-axis in case of color. Okay. So what you have to do is check this function pcolor, how you can use this. So search the internet and also the Matlab help pages so that you can use this pcolor plot. What you need is the x-axis, what you need is the y-axis, and what you need is a matrix which is the same dimension as x and y, so that lines and rows correspond to x and to y respectively. And then you can do this plotting and then do optimizations. So use a specific colorization, because the first pcolor plot which you will create will not look like this. We want that the traffic jams or the congestions are shown with red, and freeways, so situations with no congestion, will be shown with blue. And we want to have this color bar, and additionally we want to have lines here at the exits with naming of the exits, so that we know the situation here. So we have a data set from 0 to about 25 or 27 kilometers starting from Munich, and then we will have the exits here so that you can interpret the data. That's it, what you should do in the next week. So therefore, have fun with this task. I hope you had also a little bit of fun with this House of Nikolaus programming. I know that it is a very sophisticated and very hard to understand principle, but if you understood this principle of backtracking, you have understood everything about functions. So, see you in the next lesson, in the next tutorial, and have a lot of fun with these tasks, and bye bye.